In this lecture, I will continue on the development of structure based parameters using protein 3-dimensional structures. Previously, we discussed on various aspects, specifically on the structural classes of proteins. So, what are the various structural classes of proteins? All alpha proteins, all beta proteins, alpha plus beta proteins and alpha beta proteins, right. All alpha helices are dominated by alpha helices and all beta proteins, right, are enriched with the beta strands. You can see the presence of helices and strands in alpha plus beta and alpha beta proteins. In alpha plus beta proteins they segregate, right, and then in the alpha beta proteins they mix with each other. Then we discussed about the databases which contain the information on different classes, fold, families and superfamilies, etc. Right. What are major databases which contain this information? SCOP and CAT, right. And then we try to develop various parameters. The simplest one is the contact maps, right. What is the contact map?
It will give you the information regarding the closeness of two.
Right. So, it is right the giving the 3D information in the 2-dimensional form. It gives you the information regarding the contact between amino acid residues at any cutoff distance, right. What are two parameters required for constructing contact maps? Atom choice,
distance,
and the distance, right. You can either choose C alpha or C beta or any heavy atoms, and likewise you can see the cutoff distance, right, 4 angstrom or 6 angstrom and 8 angstrom and so on. So, when you have the contact maps, we can see the distribution of the residues which are in contact with each other, right, which are close in space and how far they are distributed in the sequence. Based on that, we classified the contacts into short range contacts, medium range contacts, long range contacts, right, and the long range contacts are mainly influenced with the residues which are far away in the sequence. So, now we discuss some of the examples, right. You can see the different types of globular proteins, right. All beta proteins are dominated with the long range interactions, whereas all alpha proteins are dominated with medium range interactions. Then we discussed about solvent accessibility. What is solvent accessibility?
So, how far the residue is accessible to the solvent?
Right, it will tell you the for any probe radius of water molecule, right, with the different atoms or residues in a protein, right. You can tell you the how far these residues are accessible to a solvent, right, to the van der Waals distance radius of each atom. So, then various programs are developed to get the values. What are the various programs we discussed? Access, NXS, DSSP, get area, right, and AIC and so on. So, what is the advantage of using DSSP?
It provides both.
You provide both secondary structure and solvent accessibility. What are the limitations?
It cannot give.
It gives only for the all residues, not for the all atoms, right? Fine. So, then we discussed about the pictorial representation of residues, right? So, what is the program we used to get the pictorial representation? ASA view. It will give you a spiral plot as well as the scatter line plot, right. It will give you how far these atoms or residues they have in the interior protein or at the surface of the particular protein. So, today based on the solvent accessibility, we can derive some other parameters as well as the known 3D structures are used to derive different other types of parameters, right. We will discuss some of the important properties, right, in this lecture. So, some of the parameters which I described today, so buriedness, transfer free energy, how the residues they reduce accessibility, right, from the unfolded state to the folded state, and how far they are in contact with each other. Any parameters you can quantify the contacts in a full protein, right, as well as how far these residues determine the hydrophobicity of any residues, right. We can that is called surrounding hydrophobicity. So, in buriedness will tell you the tendency of each amino acid residue to be located in the interior of the protein. So, if you see this figure, right. So, this is the ASA view of a particular protein, right. So, the grow protein. So, you can see some residues which are preferred to be on the interior of the protein, you can see here is the interior of the protein, and some residues which are at the surface. So, you have a set of proteins, right, and see whether any preference of residues which are located at the interior of the protein. So, that will give you the buriedness index of any residues. Here I varies for 1 to 20, so for the 20 different amino acid residues. So, n of I gives you the number of residues of type I on the interior of the protein, and n is the total number of residues of type I. For example, you can say n of I, right. For example, there are 10 alanines and 9 are the interior, then what is the buriedness index for the alanine?
90%.
90%, that 0.9. Likewise, you take the set of proteins, calculate the solvent accessibility, and for each residue see how many residues in all the proteins and how many residues are the interior of the protein. So, this ratio will give you the buriedness of any particular residue. So, if you relate this with hydrophobicity, earlier we discussed the hydrophobicity, what could be the relationship between hydrophobicity and buriedness?
Highly correlated.
Highly correlated, right, because the hydrophobic residues, right, they are preferred to be at the interior of the protein. So, usually the hydrophobic residues, valine, alanine, isoleucine, right, you can see the preference of these residues in the interior of the protein. They are also having high hydrophobicity. So, you can see a good correlation between buriedness as well as the hydrophobicity. Then you can also calculate transfer free energy. In this case, it will consider the preference of residues both at the interior and the exterior of the protein, right. You can see the transfer free energy, which you can calculate using this formula minus RT logarithmic of this frequency of I. This f of I you can calculate the number of residues any type I at the interior of the protein, that is interior, divided by the same type of residue I at the exterior of the protein. This will give you the relative occurrence of amino acid residues in the interior of the protein as well as in the exterior of the protein, right. For example, if you take the hydrophobic residues, what will happen?
That will be more interior.
They prefer to be right in the interior of the protein. So, you can see this f of I, that is positive. So, you can get the transfer free energy, right, that is minus RT into these are positive values, right, you will get the negative values, right. Likewise, you can see for 20 different amino acid residues, the tendency of each residue, right, to be the interior as well as the exterior of the protein. This will give you the transfer free energy of that particular residue I in any particular protein. So, then also we can also obtain the reduction accessibility. This will tell you how far this residue, right, which reduced the accessibility from the unfolded state to the folded state. So, here this is the ratio A f of I minus A unfolding of I. Here A f of I stands for the accessible surface area in the folded state, and A unfolding of I gives you the accessible surface area in the unfolded state. This will give you the ratio. Then how far it is reduced, right. In this case you subtract from 1, right, then 1 minus this quantity will give you the reduction accessibility, right. How far the specific residue which reduce from the unfolded state to the unfolded state to the folded state. So, these are the various parameters we discussed based on solvent accessibility, right. If you have solvent accessibility, you can calculate the accessible surface area, you can represent in the form of pictures, and you can derive the various parameters, right. Now, from the contacts point of view, we discuss different types of contacts, short range contacts, medium range contacts and long range contacts, and we can quantify these contacts in terms of some parameters. One of the well known parameters is contact order. Here this will classify these contacts and it will include the importance of local and non-local contacts. Local means you can see medium range or short range, non-local means you can see long range contacts. They give weightage to these contacts and they develop the parameter. So, if you see the contact order, it is given as sigma delta S of ij, where delta S of ij you can see the sequence separation. For example, here T1 first residue and F7. So, what is the sequence separation? 6 residues, right. So, likewise we add up for all the residues and normalized with the L and N, where L is the total number of residues, N is the total number of contacts. In the developing the contact order, they use all atoms and they are considered to be contacts if the distance is 6 angstrom. Okay, this is actually 6 angstrom. They tried 6, 6.5, 7 at different distances, and finally they optimized, right, to have the distance of 6 angstrom, right, between the any residues in space. So, take the T1, they construct a sphere of radius 6 angstrom. So, these are the residues, right, which are having contact any atoms with the limit of 6 angstrom. If you take T1 and F7, delta is equal to 6. Likewise, you can calculate the total separation. So, what is the total separation for this residue? 1 and 2, this is equal to 1, right. So, 1 and 4,
3.
This is 3, this case it is 2, this case 27, 14 is 6, 5, 7, right. So, you can add up, in this case sigma delta Sij equal to, what is the total value? 27, 30, 31, 33, 43, 47, 52, 58, 65, right. This is 65. This is for a particular residue. So, you can do it for all the residues in a protein, then add up everything. So, you will get a number, total number of contacts, then normalized with the number of residues and number of contacts, we will get a number. So, this is how we will quantify different types of contacts in protein structures with the one number. So, in the 3D structures, when you make the contact maps, we will make into a 2D maps. Now, here if you see this one, we will get a number. This number will tell you, okay, how far the residues are distributed in 3D structures, whether several long range contacts or several short range contacts, depending upon the length of this particular protein. So, this contact order considers all the contacts, the short range contact, medium range contact and long range contacts, but the effects they consider based on the delta Sij, sequence separation between I and J. So, then later on there is another parameter called long range parameter. It has been developed using the knowledge of only long range contacts, because several cases the rate limiting step in protein folding is how many residues which can make long range contacts. It is easy to make the short range contacts or the medium range contacts, but it takes time, right, to make long range contacts. In this case, if a protein, there are several residues which have tendency of making more number of long range contacts, that automatically it needs more time to fold. So, based on that assumption, so they developed the concept of long range order. This is from the knowledge of long range contacts. What is long range contacts?
Greater than 4.
It is a contact between two residues, right, any contacts, but they are close in space and which are far in the sequence. But far in the sequence, how far in the sequence, whether 4 residues, 10 residues, 20 residues, right. So, that we have to fix. So, in this the long range order try to use various distance cutoffs, and finally, they identified the value of 12 residues far apart. In this case, for each residue they look at the contacts and they count only if the contact residues are separated by minimum of 12 residues, otherwise it is 0. In this case, for example, if the T is the central residue, so they use the 8 angstrom sphere, they construct the sphere of 8 angstrom, and these are the residues which are located within the limit of 8 angstrom. Say aspartic acid 2, arginine 4, 328, leucine 3, A15, V6, F7 and G8. Among all these residues, how many residues which are separated by at least 12 residues? For example, this and this, so they are separated by 12 residues, and here they are separated by 12 residues, and all others they are not having 12 residues. So, in this case Nij equal to 2, and here you can see that delta sigma Nij means you can do it for all the residues. For example, D2, so you can construct a sphere around D2 and identify the residues which are occurring within the limit of 8 angstrom, and see which residues are separated by distance of 12 residues. You can add with the numbers. So, for the whole protein you can add up, right, and normalized with the n is the length of the protein, right, total number of amino acid residues, right, in a protein. So, in this case you can calculate the long range order. For example, this is the protein I showed in the last class. Okay, this is the contact residues of threonine 152 in lysozyme. So, you can see they are occurring within the limit of 8 angstrom. So, what is the value of Nij here? Right, because you have to see the contact residues and how many residues which are separated by at least 12 residues. So, here this is 94 and 152, this is 1, here this is another 1, 2 and here 1, 3. So, Nij equal to 3. For example, if you want to have the LRO for the particular residue, then normalized by the length, here T4 lysozyme is 164 residues, in this case LRO equal to 3 by 164, right, they will give the number. So, if each residue you have these numbers, then based on the numbers you can tell that, okay, how many residues which are forming more number of long range contacts. Then for the whole protein if the numbers is very high, then you can see that there are several residues in that particular protein which are forming long range contacts. So, here also you can tell you that the one number can explain the type of interactions, right, you can make in the different types of the globular protein structures. So, generally if you look at the all alpha proteins and all beta proteins, how will the LRO varies?
Higher for the all beta.
Right, it is high for all beta proteins because usually they make more number of long range contacts, right, and it is low for the case of all alpha proteins because mainly due to the short and medium range interactions. So, now first we discussed about the contact order, then we discussed about the long range order that takes only the long range contacts, and among these long range contacts and some residues they try to form more number of contacts. For example, in this case T1, how many contacts T1 has? 4 contacts, 1, 2, 3, 4. If you take second one, right, how many contacts in this case? 8 contacts, right, and the third example is very crowded, but the space is same because the distance, right, in the 3D structure that is the same, everything is 8 angstrom. But if you see this one, how many contacts in this residue has? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 contacts, right. So, if you look into these 3 different examples, which residue is more important in protein structure? Third one, right, because it is making many contacts. These contacts are influenced with different types of interactions, right. Maybe if you see the electrostatic interactions or the van der Waals interactions and hydrophobic interactions, and if you disturb this particular residue, right, and all the interactions are broken, in this case this will destabilize the protein structure as well as the stability and leave loss of function. So, then in this case you can define a parameter based on the residues which are having more number of contacts. So, this is called the multiple contact index. Here we have 3 different parameters. First one is the distance between residues, right, this is used for all the parameters like contact order or long range order or the multiple contact index, and sequence separation. In contact order they utilize the sequence information in terms of delta Sij. In the case of long range order they utilize the sequence separation, right, with the condition that to consider only if the 2 residues are separated by 12 residues. So, in addition to that, in multiple contact index they consider how many residues they have multiple contacts. So, here you see this multiple contact index they define, this is the number of contact residues with the multiple contacts normalized by n, this n is the number of residues in a protein, and nmi equal to 1 if the contacts is more than equal to 4. So, this NCI we define the radius of 7.5 residues, 7.5 angstrom, and the distance 12 residues, then we define Nij equal to 1. A 2-step procedure, first we see the NCI, there is a number of contacts based on the same as long range order, here the distance is 7.5 angstrom and the same 12 residues, and then in the same case they see how many of them have more number of contacts, at least 4 contacts, then based on that they can calculate the multiple contact index. For example, let us show an example here. This is the central residue T1 with the distance 1.5 angstrom. How many long range contacts it can make? Right, this 1, 2, 3, 4, 5. Right. In this case, NCI equal to 5 because there is 5 contacts. If NCI equal to 5, then it is greater than 4. In this case, NMI equal to 1. So, this will consider the residues which are close in space, which are separated by 12 residues, as well as the residues which contain at least 4 contacts. The numbers are not very high, so we have less number of residues are having this type of contacts, and if you see how many residues they have this type of information, they are acting as a key residues, right. From that you can see the how many key residues, the residues which are important for the stabilizing or the folding in a particular protein. So, we discussed 3 different parameters based on contacts. What are 3 different parameters we discussed?
Contact order,
long range order, and the multiple contact index. right. We discussed various parameters using solvent accessibility and some parameters about the with the contact amino acid contacts, and here we discussed about the hydrophobicity. So, earlier we discussed about the hydrophobicity scales. Experimentally you can obtain the hydrophobicity values for the 20 amino acid residues using the relative solubility of each amino acid residue in water and in organic solvents like octanol or ethanol, right, in organic solvents. So, here we will give the 20 values for the 20 different amino acid residues. But if you look into this protein environment, the behavior of the amino acid residues are not the same. Some residues they behave to be close with the polar residues and some environment with the non-polar residues. So, if you look into the protein environment and check the tendency of each residue to be surrounded with which type of residues, this will give you the hydrophobicity in protein environment. That means, each residue characterizes the hydrophobic behavior in protein environment, right. It is not just the one value for the same residues, right. See, if the threonine is here, the behavior of this threonine is different from this specific. For this is take this 1, this is take 4. So, T1 and T4 they have different hydrophobicity values depending upon the location of this residue and the residues which are surrounded by any specific residue. Based on this information, we calculate the Hj for any residue j in a protein using this formula sigma Nij, number of residues of type I which are surrounded by the residue j multiplied by the hydrophobicity index of this Hj, this particular residue. This Hj we can take the experimental value, right. So, for example, the octanol experiments or the ethanol experiments, right, and then see the neighboring residues or surrounding residues from the 3D structures. So, here we combine the experimental data plus the location of each residues in the environment. For example, we take 8 angstrom and we located the residues which are within the limit of 8 angstrom. So, what is this is the approximate values I use for different residues for simplicity, but actually we have different number experimental values for all 20 residues. So, here if you see this is the non-polar residues, I give the value of 2 and the charged residues I give -2, polar residues -1 and the hydrophobic residues 1. If you have these numbers, what is the hydrophobicity value for the central threonine? How about is D? D is -2, arginine -2, this T -1, this 1, 2, 2, 2. So, the total value will be 2, 4, 6, 7, 6, 4, 2, right. So, here the hydrophobicity value is 2, because this 2 is determined by the surrounding residues. If you have these 3 only here T4, so to get the hydrophobicity value of this T, what we have to do?
Get the surrounding residue.
We have to make a sphere, right, of 8 angstrom and then identify the residues which are occurring in this limit and substitute the values, then we will get that. So, for getting the 20 different values, same protein, different amino acid residues or same amino acid residues at different locations, you have different numbers. Now, we take the average and then you can get the average values, then you will get 20 different values. If you look into these numbers and the experimental values, some of them are you can see the correlation and some residues they have difference in behavior depending upon the location of the residues in protein environment, right. Likewise, you can calculate this hydrophobicity and this has wide applications, right, in protein structure and function. Now, I have an example, one example here. What is the left hand side? This one, this is a contact map. What is this one? This is ASA, axial surface area of different residues. So, you can see two residues, I put the for example E49 and Y35, how these residues behave in terms of contacts, axial surface area and hydrophobicity. So, we look into the axial surface area where E49 is located, E49 is here, these are the surface or buried surface, right, E49 surface. How about Y 35?
Buried. Set big.
In the
Is here,
inside.
right? It is relatively buried. Now let us look at the contacts, right? What is Y? This start from P2, D3 and so on. What is Y 35? Somewhere here or here?
Lot of contacts.
This one, right? Then where is E 49? This one E 49? What is E 49? 1, 2, 3, 4, 5, 6, 7. Yeah, I think this is E 49. So, if you look into this Y, right, how many contacts this Y has? Many contacts, right? You can see here starting from this line, right? Right. Then what is the hydrophobicity value for this Y 35? You see this is alanine. What is the value for A? This is equal to 1. So, this is the cysteine 1 and here this is glycine 1, this is glycine 1, this one is valine, this is 2 and here this is also 2, am I right? Yeah. So, here Y this is equal to 1 and here arginine is minus 2, this is R Y, or is it this one, right, R I I, this is 2 2 2 2, this is C is 2, right. So, if you see these numbers, it is highly hydrophobic and the numbers are positive, right. You can see the buried and this plus, I think it is more than 5. And look into this E49, this E49, you can see these are the residues, right. So, serine is minus 1 and here D is minus 2, right, minus 2 and you can see this is around 0, R is minus 1. So, if you look into these residues which are located at the buried or the surface, you can see the opposite trend in the hydrophobicity, which are the buried they are having high hydrophobicity, this is more hydrophobic compared with the exposed ones. Likewise, the contact also you can see here more number of contacts, because the buried here it has more number of contacts compared with the residues which are at the exposed one, for example, this E49. So, you can relate different structure based parameters which you obtain from 3D structures, right, for example, the contact maps or the hydrophobicity or the accessibility and so on. So, they are interrelated with each other.